reduced by the water, in order for something to be reduced by water, it has to have a reduction potential that's greater than that of oxygen, because of the anodic process. When water is going to give up its electrons, when water is oxidized, gives up its electrons, that's an anodic process. That's going to be occurring at this, along this potential. And so not only does it have to be greater than the reduction potential for the oxygen, it has to be .6 volts above that. And so the one that we're interested in is the E naught of cobalt 3 plus being reduced to cobalt 2 plus. That occurs at around 1.82 volts. And so this, the oxidized form of this couple is unstable in water because it is above this line. But you don't really need to worry about water oxidizing or reducing. You're not worried about the water actually reducing, acting as a reducing agent. You don't have to worry about water reducing things unless they have a really huge reduction potential. And there aren't very many things with huge reduction potentials, but all the alkali metals and the alkaline earths are way down here below the line, and so they're not stable in water, with a few exceptions. You can put aluminum and metal and magnesium and things like that. You can place them in water and they just sit there and laugh at you. Does anybody know why that is so? It's the same reason that iron, iron gradually rusts, doesn't it? But aluminum doesn't. Why doesn't aluminum oxidize the same way that iron does? Does anybody know why?
Oxidation potential is higher than
No.
Fixed utility.
The what?
So it has a fixed charge, right?
No, because it has these particular metals form an oxide layer. It actually is oxidized rapidly. Fresh, clean aluminum will immediately, when it comes in contact with air, form an oxide layer. And that oxide layer actually passivates. It's called passivating. It covers the surface so that no other oxygen can get through that layer, and it stops. Whereas when iron rusts, it doesn't form a passivating layer. In fact, the oxygen rust is a catalyst. It's autocatalytic. Once it forms, it catalyzes the further formation of rust. It opens up, gets an active surface, and it just keeps chewing away at it, and gradually will just flake off and dissolve into dust. Whereas aluminum and magnesium happen to form an oxide layer that protects them. All metals form an oxide layer. It's just not as obvious. You can't see it, but copper has an oxide layer. Zinc has an oxide layer. All of them do. But the zinc's oxide layer is not as passive. So it's more active. But you put aluminum and magnesium in acid, and they're going to go away. The reason the acid is not, this has nothing to do as much with the overpotential in this case. The reason the acid goes after it is because the acid protonates the oxygens on the surface of the aluminum and on the surface of the magnesium, and that opens it up. So if you take a piece of magnesium or a piece of aluminum and place them in acid, yeah, you're going to get bubbles. Okay. Or at least with magnesium. Okay? So I'll let this go for right now, so I won't go into any greater detail, but, well, I'll put one more reduction potential in here. 0.34 0.34 volts. So copper has a reduction potential of 0.34 volts, and it falls nicely in this range. It is rock stable in water. I can take copper, drop it into water at any pH, and it's going to be stable. Silver has 0.8 volts. It's going to be stable in water, even at very high pHs, because it's not going to go high enough above it. Essentially, we're going to need to refer to this when we start discussing some of the other problems. We start talking about electrolytic cells, we start talking about stability. This is something you should be able to do on your own for practice. And I can't emphasize that enough. This is something I want you to be able to do on your scratch paper. Practice drawing this diagram. This is what we call the stability field of water when we're referring to metals. Okay? And it's also going to be very useful when we start talking about electrolytic cells, what's going to play out, what's not going to play out, under what conditions things will play out. Yes?
The stability field is from the red line to the red line.
Yeah.
Okay.
Yeah, exactly. And generally, when we start talking about natural waters have a pH generally from around 4 to around 8 is the pH for natural waters. Okay, so you have that window. When we start, if we're going to start talking about water chemistry and what happens in lakes and things like that, and describe those processes, it may be interested in this particular slice of it. But for our purposes, we get into, in the laboratory, we have much lower pHs and much higher pHs than are routinely encountered. Okay? Yes?
To what volt does the top red line go to?
The top red line is going to go to 1.83.
So it includes cobalt in this?
Well, yeah, but cobalt is only going to be at 0 pH. As soon as that goes a little bit, the pH goes a little bit up from 0. Cobalt-3 is going to be reduced by the water. So water is going to be a reducing agent. And then where we're talking about is potential of being greater than 1.23 volts plus the overpotential. And water will reduce certain things. It'll oxidize anything below this line, red line. It'll reduce anything. It'll reduce the oxidized form of any couple above this red line. It'll oxidize the reduced form, and I know it sounds like doublespeak, but it'll oxidize the reduced form of anything below this red line. Okay? So the features you really want to keep in mind, you got to know the reduction potential for hydrogen. Oxygen's pretty easy, it's 1, 2, 3. Those two would be the ones that I would expect you to have memorized. Okay, draw this graph. Okay, that's about enough on the graph. So let's wrap the graph. Does it show up well?
Yeah, reasonably well.
Okay.
Yeah.